Alright, so in this video we'll actually work out an example of the resultant of two vectors. Now, as before, I have my two vectors drawn out in blue and green, A and B, which are oriented to one another by an angle theta, which is plotted here. And the resultant, which is drawn as the third side of the triangle in this triangle, is the r vector, and the r vector is basically a vector plus b vector, where this addition is a vectorial operation, not a mathematical one. Now, using the formulae we derived earlier in the previous videos, we found out that the magnitude of the resultant turns out to be given by this equation, the first one, and the angle at which the resultant is oriented with respect to the first vector, which is a here. That means the angle phi is given by the relation 2. Tan of phi equals this by this. So this is what we actually obtained previously, and we have derived that quite extensively. So if you are a bit confused, you might want to look into that before moving on. But anyway, we now work in just to kind of clear it all out and work out an example in this particular video. So here we have our a vector, which we assume, as we actually assumed in the previous video as well, to have a magnitude of 3 units in the east direction. So that's why I've plotted it in the horizontal direction, because my directions go as follows: east, north, south, and this being a west. And your b vector turns out to be, we can assume it to be 4 units. This is just the information that's given. And the angle that it's oriented in is the northeastern angle. That means this angle here, theta, equals to 45 degrees. So if we want to evaluate the magnitude of r vector, then that would be basically, which is this, that should be equal to, well, root of the magnitude of a square. So a is 3 units, therefore 3 units square is 9. I'm just going to write it as 3 square. We add that to the magnitude of b, and the magnitude of b is 4, so that would be 4 square. And we add this mixed term, which is 2 times the magnitude of a times the magnitude of b times the cosine of, well, 45 degrees. So right there. Yeah. So before moving on, we just want to kind of clarify the following. So cosine of 45 is 1 by root 2. If you have forgotten, it would be helpful at this moment to review your trigonometric tables, but if that's not possible, take my word for it. This is 1 by root 2. If you want to evaluate this expression, well, it would just be 9 plus 16, that's 4 square, plus 2 times 3 times 4, so this makes 12. 12 times 2 is 24. 24 by root 2 is 12 root 2. The other way to look at this is you divide, you can kind of cancel out root 2 from the denominator and root 2 from the numerator. That's left with 12 times root 2. So that's one way to evaluate that. You can further simplify that to 25 plus 12 root 2. You can be content with this answer, which yields that the length of this red vector must be 25 plus 12 root 2 whole to the power 1 by 2. That basically, that means we take the under root of that expression, and that must be this entire length. If this length here is 4, this length here is 3. Now, with that in mind, we can actually proceed on, but let me just calculate the length in decimals just for the heck of it. So we're adding 25 to, and I'm doing this on the calculator, so it might take a while, 25 plus, well, 12 times root of 2. That should yield something, and we take the root of that. That should give you, well, it's a odd number. It's quite weird. It's actually 6.478, and it goes on and on and on. That should be the case because it's an irrational number, because we have an irrational number within our, well, expression. So anyway, this is an irrational number. The length of the vector must be this, but what must be, is it just a number, or is it something else? Well, we know that b here is 4 units. Well, it's s here, it's a plural, and a here is 3 units. That means this must be somewhere, this as in the vector R must be somewhere around 6.478 units. So you want to ensure that the length is measured in the units of length, and the units of length here, well, it's units. Anyway, with that out and known, we can proceed on to evaluate something more interesting. And the more interesting part turns out to be, may I just get rid of this for the moment? I can do that. Let me just write it again. So the magnitude of R turns out to be 6.478, well, that's an approximate value, units. So that's what we evaluated so far using 1. Now we want to invoke a second relation that gives us the value of, well, phi, right? So tangent of phi should be equal to this by this. That means numerator by denominator. Now let's write down each and every term one by one and try to evaluate what it turns out. So b modulus here is nothing but 4, and sine of theta is sine of, well, 45. Same thing in the denominator, you have a, which is modulus of a, which is 3, and you add that to, well, b, which is 4, and sine of theta, which is, oh, I'm so sorry, this must be cosine, so that's a mistake here. Let me just get rid of that. So there's a mistake. This is how it's written. It must be cosine of theta. Now, the way I remember this and the way I was able to point to this incorrectly, because tangent equals sine over cos. So sine over cosine of the same angle. So this is how we write tangent of the value. And we kind of retain the same ordering. That means the sine theta ends up in the numerator and the cosine theta ends up in the denominator. The only difference here is in the expression, that the expression actually takes into account the angle theta, not phi. So that's one to remember that. So it must be sine over cosine. There's no reason for having it being sine over, well, sine. So that's incorrect. So this would be 4 times cosine of 45. And that should give you, maybe you might want to change the color. So right, so work that out again. 4 by root 2 divided by 3 by 4 by root 2. Let me evaluate that on the calculator once again. So there's 4 divided by root of 2. Now I must add that to, well, to 3 in the denominator. So let's see how that turns out. That turns out to be, well, a pretty decent value of 0.485. Now this is a unitless term, because it's basically the same thing divided by the same thing. It's just a number. It's just a number. So I don't need to be writing this in terms of what unit it has, what, things like that. So I don't really need to bother about anything else. It's just the numerical value that I'm concerned about. But should that be enough? Do I really need to evaluate tangent of theta? Well, no, I need to evaluate what theta is in terms of degrees. So I must take the tan inverse on both of the sides. So I take the tan inverse on the left-hand side, I take the tan inverse on the right-hand side. Tan inverse of tangent of theta is, well, I'm sorry, phi is phi. So it's taking the inverse of a function, gives you the value inside, so that leaves you an identity. And tangent inverse of 0.485 is equal to, let me evaluate that as well. Well, that turns out to be a good handsome 25.886 degrees. So that is what we finally end up getting. Therefore, this angle here is at 25.886 degrees. That's a very close approximation to the orientation of R. So that was a video. We basically invoked and applied these two equations, these two expressions, and we ended up with a resultant. Now the thing is, we now know every single detail about the vector R, and that was our intention at the beginning of this video. So we know the magnitude, and we also know the direction. The magnitude is given by the expression of 6.478 units, and the direction is given by phi equals, well, 25.886 degrees. So that means we have all the information about our resultant vector. So we must be very proud of ourselves at this moment, and this is how you use the formulae. So I hope this video helps, and all the best.